Welcome back, students. We're going to continue our discussion of modeling linear functions, and we're going to focus in now on how do you handle it when you've got data and information that looks linear, but the points don't form a perfect line. So what we're going to do in those cases is we are going to still create an equation to model what's happening. We're going to recognize that our equation isn't going to create perfect predictions because there is some variability in the data not lining up perfectly. But the model that we'll create will be still useful for getting reasonably accurate predictions. So if we're finding this, what I've just been talking about is called a line of fit. We're going to create a line that roughly fits the data. First, you make a scatter plot of your data. Then you're going to sketch a line that most closely appears to follow the trend. A good way to figure out if you're following it pretty well is that you'll have about the same amount of points above and below the line, and they're going to be scattered about. Okay, we don't want all of the points that are below the line to be in the second half and all the points that are above the line to be in the first half. No, we want them a roughly the same amount above and below all throughout the line. Okay, then we're going to choose 2 points on the line to estimate points for our line to be able to calculate slope and y-intercept. And then we're going to write the equation of the line that passes through those 2 points. Okay? All right, so let's take a look at our first problem. The table to the left is showing the femur length in centimeters and height in centimeters of several people. Do the data show a linear relationship? If so, write an equation of a line of fit and use it to estimate the height of a person whose femur is 35 centimeters long. So we've got our data. Now from this data, we created a scatter plot. Looking at this scatter plot, you can see that not all these points are lining up perfectly with that line. However, the points are clearly creating this linear relationship. So we then drew a line that, to our best ability, matched the data that we saw, and picked 2 points that are on that line. Now, when you're picking these 2 points do not have to be points that were in your previous table. Sometimes when you draw your line of fit, it doesn't go through any of the points that were previously drawn on the scatter plot. And that's okay. You would just pick 2 points along the line that you drew. All right. So we're going to use these 2 points now to find slope. So our slope is going to be the change in y values, 195 minus 170, over the change in the x values, 50 minus 40. So that should give us 25 over 10. So we have a slope of 2.5. Now we can use our point slope form to find the equation. So y minus y1, let's go ahead and use those points. The numbers are ever so slightly smaller. So y minus 170 is equal to a 2.5 times by x minus our x1, 40. Okay, let's solve for y. So we'll add the 170 to both sides. And we'll get 2.5x minus 2.5 times 40 is going to be 100. And then we added our 170. So to simplify that, 2.5x plus 70. Great. Now, we've got our equation. We can now use it to estimate the height of a person whose femur is 3.5 centimeters long. So they gave us the femur length. Femur length is x, and we want to figure out height. So I'm going to take this 35 centimeters, that is an x, and put it in there. And now we can figure out y, the height. So 2.5 times 35 plus 70, that is going to give us 157.5, approximately. Or nope, I didn't round anything. So yes, it's exactly. So the height, let's see, height was in centimeters. So this person would be we would predict they would be 175.5 centimeters tall. Okay, so once again, things like people's height compared to something like their femur, yes, these are strongly related, but there's still going to be variability. Okay, but still, if we know the femur length, we are likely to know how tall they would have grown. Now, this is estimating, and frankly, it's a lot of work for us drawing a line that looked good enough to us. There exists another way, and that is going to be using what is called a regression line. Calculators, online calculators and graphing calculators can usually calculate this. And what it does is it gets the line as close to all the points as it possibly can. And it also calculates a coefficient to say how closely it was able to do that. So what we're going to do is use a calculator to calculate one of these regression lines for the problem that we saw here in example 3. We're going to use a linear regression feature on a calculator to find the equation of a line of best fit. So not a line of fit, a line of best fit for the data in example 3, and then estimate the height of a person whose femur is 35 centimeters long. And then we'll compare it to what we got up here. All right, so let's go ahead and get to our TI calculator. One thing I am going to do, it's not going to tell me my correlation coefficient unless I turn on diagnostics. So I'll quickly show you how to do that. Click second, and then 0 opens up the catalog. Now I want to get to the diagnostics. So I press this for D, and I want to go to diagnostic on. Hit enter, enter again, and I've got diagnostic on. All right, now in order for it to calculate the line, it needs to have all the data from the table. So I'm going to go here to stat, edit, and I've got my lists. Now I'm going to type all those numbers into my list. Oops, 151, 185, and 182. Great. So I've got all those numbers typed into my calculator. Now what we're going to do, so once again, all of this is to do with statistics. So we'll go over here to statistics, and I want it to calculate things. So we're going to do a linear regression. Notice it's got it in the MX plus B form, even though they used A. That's fine. So lin reg for linear regression. So I'll go there, press enter. I typed all my X values into L1, so that's perfect. All my Y values into L2, so that's perfect as well. And I don't need to worry about those other things, and I'm just going to click calculate. Okay, so it has given me this equation. It's telling me that my slope A is a 2.6, the y-intercept B is a 64.99. The next thing I want to pay attention to is the R value. So this one right here, this is why we turned on diagnostics. The closer this number is to either a positive one or a negative one. So it only goes from negative one to positive one. The closer it is to zero, there's not much of a relationship between the numbers you typed in. But the closer it is to positive one or negative one, it suggests that there's a very strong relationship. We are very close to one. We can expect that this equation is going to be fairly accurate and fairly good at making its predictions. Okay, so let's go ahead and take this information and write it down. So we are going to have an equation that is y is equal to 2.6x plus, and we're going to round that one up to 65. So there's our equation. And now let's do that estimation again for 35. So let's do y is equal to 2.6 times by a 35 plus 65. Okay. And then that should give us 156 centimeters. Okay, so actually our prediction from our line that was just drawn is fairly close to this highly accurate line of best fit. This prediction is ever so slightly lower. Okay, so we estimated the height. We compared it to what we got in the previous example 3. I hope this has helped you to understand how to work with the TI calculator to find these lines of best fit. Other great resources are calculators like Desmos. Just make sure that whatever calculator you're using, if you're going to be that you know how to use it and you know how to do a linear regression on it when you come take the assessment for this, when you come in for your proctored assessment. And while I do love Desmos as a calculator, and I think it's great as a learning tool, you won't be able to access that one while you're taking your proctored. So keep that in mind.